Good afternoon, and thank you for being with us today. Today we are pleased to welcome Dr. Atef Elsherbeni. He is a professor and development distinguished chair in electrical engineering department at Colorado School of Mines. His specialty in electromagnetics, especially in computational electromagnetic using finite difference time domain, in addition to antennas, reflected and braided arrays, antennas. And today he's going to share with us his presentation. So with that, please pay attention to Dr. Atef and let's welcome him. Dr. Atef, the floor is yours.
Okay. Thank you, Dr. Abdullah, and thank you all for coming and getting ready to hear a little bit of what I'm going to describe today about numerical technique, specifically using the finite difference time domain for solving electromagnetic problems. As Dr. Abdullah mentioned, I am with Colorado School of Mines, and previously I was University of Mississippi for so many years before I moved to Colorado School of Mines. So today we are going to talk about numerical techniques, and this slide here summarizes basically the two forms of Maxwell equations from which we can develop any electromagnetic solver. You can see on the left here the integral form of Maxwell equations, and on the right you can see the differential form of Maxwell equation. We can easily combine solution based on integral form and differential form. And in addition to this, we can combine techniques to work either in time domain or in frequency domain. Most of the time, the integral form is used for midst of moment, boundary element, and finite integration, finite element techniques. And most of the time, the differential equation are being used in finite difference and finite volume and finite element technique. So any one of those common technique can be used in time domain and frequency domain. And today we're just going to focus on finite difference in time domain. So if we start with the two differential equation, what you see them here is most of the time they are listed in textbook, but I am listing them here in a full form in which we are including the electric conductivity, magnetic conductivity or losses, and impressed electric current and impressed magnetic current sources. The way we present it this way is basically a full way of representing Maxwell equation that would allow us to later on get a solution in all these parameters, and we don't have to change the form of the solution and efficiently compute our solution for any kind of problem. Obviously, we see that these are two curl or vector equations. We can expand them in Cartesian coordinate into 6 equations. You can see those 3 scalar equations here. They are developed to solve for the electric field component, Ex, Ey, Ez, and on this right side here for Hx, Hy, Hz. You notice on the right-hand side here, differential with respect to time. On the left-hand side, differential with respect to time. On the right-hand side is differential with respect to space coordinates, X and Y and Z. So basically, if you look at any one of those 6 scalar first-order differential equation, they combine at least 3 field components. And there is no way we can take 3 of those equations and solve them together. We have to solve all 6 equations together if we were to solve for a 3-dimensional problem. So how we do it in a finite difference time domain is basically we set an environment, and this environment is going to be bounded by boundaries. The boundaries are here, basically the blue box here. Any kind of cell in the domain, I'm going to give it the indices IJK, and the entire domain is going to start with cell 1, 1, 1, and end with cell NX, NY, NZ. So imagine that I have 10 cells, or let's say 100 cells in the X direction, 100 cells in the Y direction, and 100 cells in the Z direction. We are going to end up with 1,000,000 cells in this domain. For those 1,000,000 cells, we need to solve for each cell the 6 unknown field component Ex, Ey, Ez, and Hx, Hy, Hz. So basically, we need to solve those 6 equations for each node, or in other words, for million cells if we have 1 by 100 by 100 by 100. Okay, where do we locate the field component relative to the cell itself? A cell like this, we are going to look at the lower left corner, and that corner we are going to identify it with the coordinates of the cell itself, IJK. And then any edge of the cell that connects to this node is going to have in its middle the field component, electric field component. So this edge and this edge and this edge, they all contain the Ex, Ey, Ez. And if you also look at this entire cell, if you look at the 3 faces that connects at this point, you can see the front face, this left face, and the bottom face. Right into the middle of those faces are the magnetic field component associated with this node. From the bottom face, we can see that this is Hz, this is Hx, and this is Hy. So for this cell identified by IJK, we have those 3 electric field components, and we have those 3 magnetic field components are the unknown associated with this node. All other field components, you see it here, are associated with other nodes in the domain. Okay, now the arrangement that you have seen it with a node at this point with Ex, Ey, Ez at the edges, and Hx, Hy, Hz are going into the middle of the faces. You can easily see, for example, if you look at the Ez component, you can see it is surrounded by circulating magnetic field. If you look at the Ex component, circulated by surrounding magnetic field, and the Ey component also surrounded by circulating magnetic field. That's going to help us tremendously in applying the Tuchel equation in terms of Ampere and Faraday's law. Now, and also to solve any magnetic problem, we need to define the permittivity and permeability. And where are they going to be defined? They are going to be defined, electric permittivity is going to be defined where the electric field is. The permeability is going to be defined where the magnetic field is. The same way we're going to define the electric conductivity where the electric field is, and magnetic conductivity where the electric field components are located in the domain. So with this, let's go back to the Tuchel equations, their expansion in terms of 6 scalar equation. And let's see how are we going to be able to translate all these 6 equations into a form that's suitable to program and to develop it in a computer program and produce some solution. We notice that we have first derivative with respect to space or time. And for any one of those derivatives, we are going to use the central difference approximation, which will give us a second order accurate solution. We are going to do this for differentiation with respect to X or Y or Z, and also for differentiation with respect to time. The differentiation with respect to X or Y and Z are going to be identified by evaluation of the field components, 1/2 delta X over 2 from one side, and 1/2 delta X over 2 on the other side. So the value of the 2 field component around the point at which we are going to evaluate the derivative is going to be evaluated. We can do the same thing for Y and Z as well. But for time, the identification of time is the superscript n. And if I'm differentiating this function with respect to time, imagine that this is the axis time. I would like to differentiate it with respect to time. If I am advancing the time by 1/2 delta t and reducing the time by 1/2 delta t and dividing by delta t, then I'm going to get the derivative in the middle here at time t. So basically, using this, we also need to know the arrangement of the field components so that we can correctly represent the derivative with respect to Y and Z and X as well. For example, here is one of the 6 equations. And this side, I have Ex component, and I'm going to differentiate it with respect to time. On this side, if I'm doing any differentiation, I need to differentiate it at the position of the Ex component. So the derivative of Hz, for example, which is this component, I need to differentiate this using central difference where the derivative is located as the position of Ex. So the derivative has to be here. So I need to take this HZ component and the HZ component from this cell, the other cell that's not shown here, and the central difference between these two are going to give me the value of the derivative of HZ with respect to Y at the position of Ex. The same thing, we are going to do it for HY. HY is here, and I need to differentiate HY with respect to Z axis, and it need to be at the position X. So I need this component of HY, this component of HY, they are going to be subtracted from each other and then divided by delta Z, give me the derivative of HY at the position Ex. So keeping this in mind that every term here has to be positioned at the position of Ex, that's basically those four components of H are going to be used in those differentiation. These values, we can evaluate them at any point in time as well. So expanding on this, this is the same equation. Now let's look at the derivative for Ex. When I differentiate Ex in terms of Ex at n plus 1 and Ex at n, this is the current time t, this is the future time t plus 1. So this derivative should be at the future time t plus 1/2 delta t. For this reason, every term in this side of the equation should be evaluated at n plus 1/2. So, and it is easier to evaluate all the electric field component at integer values of time and all the magnetic field component at integer plus 1/2 value of time. So for this reason, we come to this E component here, and we take an average between En plus 1 and En over 2 to represent it as En plus 1/2, because it is located on this right-hand side of the equation and should be evaluated at En plus 1/2. So once we do this, we can look at this equation one more time. You can see it is a very simple equation. It doesn't have anything other than addition, subtraction, multiplication, and division. The unknown quantities is Exn plus 1 and Exn plus 1. We just rearrange the equation and we get all the coefficient multiplied by Exn plus 1 on one side, which is this, and everything else that we know is here. So this is our new value of Ex at a time t plus 1 delta t in terms of previous values of E and H components. Now I can divide every term by this coefficient and reach this is approximation, this approximated value here after approximating the derivative, which basically tells us that the new value of Ex is coming in terms of the old value of Ex in time times a coefficient. And this coefficient is this term here. This coefficient is this term, and this coefficient is this term, and this coefficient is this term. Now, these coefficients, they don't depend on time. The delta T is a constant quantity, conductivity is constant, permittivity is constant, and so on. So I need to solve this equation for all time steps that I'm going to do. And remember, I gave you the example of 100 cell in each direction, and that is going to lead into 1 million cell. At each point, we need to solve for 6 unknown values, so basically 6 million values, and we need to repeat this for thousands of times. Most of the time, 5,000 times, 6,000 times, depending on the problem itself. So you can imagine how many times we are going to execute this equation. And for this, because we are going to execute this equation so many times, we evaluate all those coefficients one time before we do the time iteration, and we store them in 3-dimensional matrices like what you see it here. The M here is an indicative of IGK, abbreviation of IGK, and we evaluate this matrix, this matrix, this matrix, this matrix once, and then repeatedly evaluate this equation so many times, 6 million, time 1 million, so that we can get the solution for Ex. We do the same thing for the EY and EZ, and we also generate coefficients, and all the coefficients that are related for the electric field component are listed here. Whatever we did for the electric field, we do it for the magnetic field, and these are the corresponding coefficients. So now, knowing those 3 equations, and those 3 equations we have the solution for all unknown field component in a very, very simple form. What comes next is how to program it in an efficient way to speed up the calculation for the problems that you would like to solve. I explained to you how we get all the field component for a three-dimensional configuration. We can reduce this into a two-dimensional configuration in which we will be able to separate three equations together and three equations together. Each one will be identified as a transverse magnetic or transverse electric field, in which this TM to Z is going to have EZ and HX and HY. In the TE to Z, I'm going to have HZ and EY and EX. The same way you can reduce the two-dimensional problem into one-dimensional problem. In each one of them, you are going to have only two field components to solve. But you have the solution for the three-dimensional problem, and it's very simple to reduce it to two-dimension and one-dimension. So the solution or any program to be written for this kind of analysis start with the definition of the problem space and define the parameters. Those parameters are permittivity, permeability, electric conductivity, magnetic conductivity, and sources. And of course, the configuration or the object that you would like to put it in the computational domain. And then compute all the coefficients that I showed it to you in the previous slides. And then compute some additional parameters that are required for what we call it CBML to terminate the computational domain. Well, I'm not going to touch on this here, but it's basically for the entire computational domain. And instead of computing everything all the way to infinity, which is not possible, we terminate it by absorbing boundary. The best absorbing boundary we use right now is CBML. And then we start the time loop. You can see this is the time loop here, in which we update the magnetic field component at 1/2 delta T, and then apply some boundary condition magnetic field component, and then increment the time with another delta T over 2. Then we update electric field component, apply some parameter for the absorbing boundary for the electric field. And then we increment the time by 1 delta T, and we continue the loop. While we're doing this, we output some data, we store this data, and once we are finished from the loop, we can look at the data and post-process it. This data that we output from the time domain, we can output it in time domain, and we can also output it when the time domain, when the time loop is finished as a frequency domain, because we can perform FFT or discrete Fourier transform while we are doing the time iteration as well. So this is basically the entire program and the entire formulation, especially except for special cases. And some of those special cases is if you would like to include circuit elements into the electromagnetic simulator. For example, if you would like to have a voltage source with internal resistance, assuming, for example, this is a port of an antenna, and you would like to excite this antenna with a 50 ohm signal with internal resistance 50 ohm and a signal Vs. Then we need to have a representation for a voltage source like this in the electromagnetic simulator. To be able to do this, we start looking at the current going between the two nodes and divided by the cross-section area. That gives us the impressed surface current density. And if you remember, we had a last term in the updating equation is related to the impressed current density. And we basically go through similar formulation to end up with an updating electric field along the nodes between IGK and IGK plus 1, which is the easy component, in the same form as we have done before for the easy component, with coefficients are filling the same kind of matrices. The only difference is that the coefficient at the position between these two nodes are going to take this form rather than the previous form. So adding a voltage source with an internal resistance doesn't require any additional serious formulation other than having the coefficients at this position updated with those expressions. The same thing, we can do it for a current source with parallel resistance. And the same thing, we can do it for an inductor and capacitor, and obviously resistor as well. So the formulation for all these are very simple and straightforward, and we can put them in the safe form. So let's look at some examples. Here we have a piece of conductors, this red one, and a resistor here between these two conductors, and a voltage source with a sinusoidal waveform identified by the blue curve here, and internal resistance equal to the resistance of this load resistance here. So this simple circuit is nothing more than a voltage divider. The voltage coming out of this voltage source is going to be divided by the between the internal resistance and the load resistance. And since both of them are 50 ohm, then whatever comes out of the source is going to be divided between these two resistors. So if I sample the voltage across the load resistor, I'm going to end up with this dashed red curve here that give you basically 50% of the total voltage coming out of the voltage source. These two curves that you see here are not coming from a circuit theory. They are coming from an electromagnetic solution of Maxwell equation. All what we did here is we updated the 6 field component, Ex, Ey, Z, Hx, Hy, Hz, and from E and H, we capture voltage and we capture current. And that's what you see, the voltage are being captured here and the current are being captured here. So no circuit theory at all is being used, completely Maxwell equation to produce these results. The same thing, we do it here. We have a voltage source with internal resistance. This time we put a step function as a signal coming out of this voltage source. And we do have an exact solution for a source connected to a capacitor. And you can see the exact solution is represented by a dot. And the blue curve is basically the sample voltage from the finite difference time domain solution across the capacitor. The same thing for an inductor as well. Here is an inductor, 2 pieces of conductor connecting the inductor to the voltage source with the internal resistance. Okay, I showed you inductors, capacitor, resistor. Now let's look at some nonlinear component. Can we do also this in a finite difference time domain? And the answer is yes. And here is some example. Again, everything here is basically solved using Maxwell equation. And you can see the sample voltage across the diode here is being clipped down, like what you see it here in the dashed red curve, while the source is producing a sinusoidal waveform by the blue curve. You can also see that we can add a capacitor in series with the diode, and the diode is going to be turned on and off, and the capacitor is going to be charged only when the signal is going through. So you can see the incremental charge of the capacitor in one direction, and if I reverse the polarity of the diode, then you can see that this charge is going to happen in the opposite direction. So all what you see here is basically captured voltage and current from the finite difference time domain simulation for these circuits. Now, time domain is not going to obviously give you impression right away that I can get a very good frequency domain solution for a problem. But in fact, we can look at a problem like this where we have a voltage source here, sinusoidal waveform operating at 5 gigahertz, and we have a diode and resistor, and we know that the diode is a nonlinear component. When we sample the voltage across the source, we can see a good sinusoidal waveform, and when we sample the voltage across the resistor, we can see this red curve here, and obviously the diode is clipping the bottom portion of the signal. Now, this is the signal that's being captured across the resistor as a function of time. When we take it, this is again comparison between the signal across the resistor using the finite difference time domain and using ADS. I'm sure all of you knows how to use ADS. And then when you convert it to time, to frequency, you can see the signal that comes out of the source as a 5 gigahertz has only one harmonic, which is at 5 gigahertz. The signal that we capture across the resistor as a function of time, when we take it to frequency domain, we can see the fundamental frequency as 5 gigahertz, and all other harmonic are also showing up. So using a finite difference time domain or a finite difference solution in time domain, you can also predict and use or use the results that you get it in time domain to identify solution in a frequency domain and much wide frequency range. We obtained all these results by only one simulation in time domain. That's the main difference between solving a problem in frequency domain, like when you use finite element, for example, in HFSS or some other solver where they rely on integral equation and frequency domain solution. You have to do the solution at every frequency if you would like to get a solution at a wide band. In a finite difference time domain, you do the solution only once, and you should be able to get multiple frequency solutions. Again, to compare the harmonics with ADS and the finite difference time domain, you can see a very good match here to confirm that what we are doing is correct as well. That's a comparison with the amplitude value. This is a comparison with the phase value and also good agreement. I'm gonna give you also a little bit more complicated structure to show you how we can use finite difference time domain in some microwave circuits like this. Again, the voltage source at 5 gigahertz, the terminating resistance, a parallel diode that is gonna introduce some harmonic in the system. But now I'm gonna put a low pass filter on this side. So whatever non-linearity comes out of this diode is gonna affect the signal coming to the resistor, but it's not gonna go back to the source. So if I capture the voltage across the source, I'm gonna end up with the blue curve here. If I'm gonna capture the voltage across the resistor, I'm gonna end up with the red curve here. If I take these two to the frequency domain, again, I'm not gonna see any harmonic at this port here, but I'm gonna see all kind of harmonic from the sampling of the voltage across the port out here. The image that you see it here is exactly the image that is being used in the simulation in the finite difference time domain to basically solve for E and H, and later on to capture the current and the voltage at these two ports. Now let's look at the much more complicated circuits, an amplifier. Can I put an amplifier in a finite difference time domain code? And the answer is yes, if we can come up with an updating equation for dependent sources. And there are 4 types of dependent sources. You can have voltage control voltage source, voltage control current source, current control current source, and current control voltage source. We have come up with updating equation for all dependent sources as well. And once we have those equations, if we can translate the amplifier equivalent circuit into a circuit like this, each amplifier has its own equivalent circuit. We can put this equivalent circuit into the finite difference time domain grid, and we can do a solution. For example, here is a solution for an op-amp amplifier with those resistance here. This configuration works as an amplifier for the input signal at port 1 to the output signal at port 2. And you can easily see that port 1 signal here, a magnitude and its amplification here. All this is coming from a finite difference time domain simulation. You can also at the MOSFET representation with a much more complicated equivalent circuit for the MOSFET. But again, you can see that the results at the output port here for a sinusoidal waveform here is exactly mimicking the result that you can get it with a PSpice simulation. If we look at the BGT configuration, and again, if we look at the equivalent circuit and put it in the circuit here, and you can see the amplification that we obtained with the electromagnetic solution of Maxwell equation for this equivalent circuit. So with this, I ended up basically showing you most of the common equation for solving traditional problem, and also for equations that solve for circuit elements that whether they are linear or nonlinear or much more complicated like amplifier components. Now let's look at how we improve the solution in the computational domain. We're going to start using non-uniform discretization. And the reason for this, if you have a configuration like this is just a very generic configuration. You can get a good solution for it, but not with this coarse mesh, with this fine mesh. But if we make a small mesh around the areas where we have variation in the configuration, like here and here, and everywhere else we have coarse mesh, we can get the same kind of solution from this configuration as we get from this solution. The difference is the number of meshes here or nodes here and the number of nodes here. Remember, if I reduce the number of nodes, each node is associated with 6 field components. I'm tremendously reducing the number of computations. So basically, we need to develop an algorithm in which we can have a fine mesh in certain area in the domain and a coarse mesh in other areas in the domain. And we have done this by transitioning from the coarse mesh to the fine mesh with a gradual decrease in the mesh size so that we cannot introduce artificial reflection from the sudden transition from coarse mesh to fine mesh. And we did this, and we have some examples here for this patch antenna, where you can see around this area here and this area here where we have the probe excitation, and this edge here, we have fine mesh. Other places we have coarse mesh, and you can see that the blue and curve results are basically on top of each other, coming from a fine and non-uniform discretization. The coarse mesh everywhere gives you a little bit shift of operating frequency. With this non-uniform discretization, we saved the computation time from 33 minutes to about 20 minutes, and the storage also, number of cells from about 277 million cells to 181 million cells. So saving in memory and saving in execution time as well. Here is another example for a filter problem. Again, very good comparison between the result from the non-uniform and the fine mesh, and the saving time in minutes. You can see here 1800, and this is 460, almost 3 times saving in time, and also saving in memory is about 3 times saving in memory. Okay, so in addition to this, we can look at some configuration in which the material itself is not going to be having constant parameter as a function of frequency. For example, if you have a dispersive material, in other words, the permittivity, permeability, for example, of this material is going to change as a function of frequency. If it is going to change as a function of frequency, then it is going to be harder to describe it in a time domain solver, because most of the time in a time domain solver, we use a waveform to excite the domain, and this waveform has multiple frequencies, and for each component of those frequencies, we need to define the property of the material inside the domain with the right property for that frequency. So for this situation, we have to look into a completely different formulation, not completely different, but a formulation that we can call it dispersive finite difference time domain formulation. That formulation is going to take into account the variation of the permittivity, for example, as a function of frequency. For example, here we have material that the real part of the permittivity is varying as a function of frequency from basically 1 to 5 gigahertz, and the imaginary part of the permittivity is also varying. So it's a complex permittivity that has real part and imaginary part. The easiest way to represent this in a finite difference time domain solution is to represent it in a form like this. This form is called the Lorentz parameters, in which the permittivity as a function of frequency is represented by some parameters here, and those parameters are basically epsilon s and delta 1 and omega 1 and epsilon infinity. So there are so many other parameters like Lorentz and debye, and we use debye a lot, and we applied debye representation of the varying permittivity for dispersive media. And here is one example of a plane wave scattering by a dispersive sphere, and we can have an exact solution for it. So the exact solution is represented by the dashed or the dotted line, and the finite difference time domain solution is basically represented by the plus and cross and the dot here. The solid line also is an exact solution. So you can see a very good comparison in 2 different plane cuts. And you notice that we are representing the solution at 1 gigahertz, 2 gigahertz, 3 gigahertz. The finite difference time domain solution ran only 1 time to produce the result for all these 3 frequencies, and we had to run the exact solution 3 times each time at one frequency to be able to get the results and compare them together. So there is tremendous advantage of having a dispersive finite difference time domain solver as well, in which you can run the solution and time domain for multiple frequencies. And I'm going to show you some example, practical example of this, and you get a solution for multiple frequencies at once. So to be able to do this, and some of the examples that we have worked with is the human tissue, specifically human head. And about 20 years ago, we developed this correlation between the variable permittivity as a function of frequency for all these different types of tissues, of human tissues, as a function of the Bioheat equation, in which we use 3 terms. So you can see here 3 deltas and 3 taus, 3 taus and 3 deltas. And once we have developed those numbers, you can use all these things in the dispersive finite difference time domain solution, and you get solution all the way from 500 megahertz all the way to 200 gigahertz. Right now we are, 20 gigahertz. Right now we are extending those parameters, and we have published a recent conference paper in which all these parameters are being extended from 20 gigahertz all the way to 100 gigahertz. And the reason for this, because of the millimeter wave and all kind of antennas that you start seeing it operating at 60 and 80 and 28 gigahertz, specifically 24 and 30 gigahertz antennas that are for 5G applications. So one of the applications is that we can represent the human head into the finite difference time domain, computational domain, by taking MRI images and discretize it and represent it in the computational domain. In the MRI image, we use all these tissues, and we use those parameters out of this table to represent them in the finite difference time domain. And basically, we put those are the parameters for the tissues that we use. And in addition to the electromagnetic simulation, we also another equation called Bioheat equation, in which we can calculate the specific absorption rate being absorbed in the human head. And from this SAR, we can calculate the temperature inside the human head, and we calculate the temperature rise between a human head exposed to the electromagnetic wave and not exposed to electromagnetic wave. So basically, to do this, we use those 8 tissues. And in one simulation, we use 0.9 millimeter resolution. In other simulation, we use 2 millimeter resolution based on the application itself. For example, in this application, we needed to define an antenna to mimic multi-frequency operation that we are going to put it closer to the human head. So we put a dipole antenna with 2 parasitic elements and working at 0.9 or 900 megahertz and 1.5 gigahertz, specifically designed for those 2 frequencies of a cellular phone operation. And we put, and the SAR equation is evaluated from electromagnetic field quantities, and the temperature is evaluated from the SAR using this equation. And we put this combination of the antenna closer to a human head, and we calculated the temperature rise. And you can see at 900 megahertz, basically, you can see those 3 curves here are centered at 900 gigahertz and plus or minus 5 or 10% of the frequency. And those 3 lines here represent the temperature rise at 1.5 gigahertz. You can easily see that the temperature rise in terms of centigrade reaches about 0.25 centigrade here and 0.15 centigrade at a higher frequency. At a higher frequency, the penetration of the field inside the human head would be smaller. And basically, the temperature rise also is going to be smaller. You notice after about 25 minutes of exposure that everything settled down, and that's basically temperature rise that you're going to see. To confirm this, you can see here the temperature distribution and also the SAR distribution inside the human head at 900 megahertz and at 1.5 gigahertz. Again, the depths of the strength is smaller at 1.5 gigahertz relative to 900 megahertz. In addition, application is that we said most of the smart glasses right now are going to have antennas. So why don't we try to mimic this smart glasses also and put an antenna here on the bridge area or in the side arm and see the effect of those antenna on a human head. So we had glasses like this in which we simulated every piece of it, the arm, the frame, the lens, and even the metal hinges here. And we generated this kind of antenna that work at 2.4 and 4.9 gigahertz, supporting Wi-Fi and 5G cellular operation frequency. And we put them at one time in position 2 in the bridge and one time at position 1 in the side arm. And again, in this simulation, we use 0.9 millimeter discretization for the human head tissues. And you can see that in position 1 and position 2, the response of the antenna itself operating at the 2 designated frequency and the corresponding temperature and SAR and the radiation pattern at 2.4 and 4.9 at this position 1. The same results or similar results were obtained when you have the antenna at position 2. Similar observation as we had observed it before, but different levels of SAR and temperature rise. Basically, you can see here that the temperature rise can reach up to 0.35 centigrade. And you can see the improvement or the performance of the dispersive code over non-dispersive code can reach up to 60% if we are calculating for 8-time values of the frequencies in one run. So 60% enhancement of the performance for only 8-time. And if we need to calculate at more frequencies, this curve continues, but not steep beyond this point, but definitely is going to be above 60% performance. In terms of visualization, finite difference time domain is very, very good in visualizing field, how it acts. And this is a very nice feature to be able to examine your solution and know if you are doing the solution right or not. For example, here I have a pulse in the middle of free space bounded by 2 perfect electric conductors propagating in both directions. And after 300 time steps, at 615 time steps, the pulse started to reflect from the BEC. You can see the electric field reverse polarization, and the magnetic field did not reverse polarization because of the reflection coefficient of a BEC. To represent this in this should have a movie to run.
Sorry for interrupting.
Yeah.
I think we have almost 3 minutes.
Okay, so we'll skip the movie. I don't know why it is not working. And here is another image of wave propagation through a dielectric media. And this one here shows you the animation in this movie. I'll skip this one here, but these are 2 snapshots of a cylindrical wave scattering from a square BEC cylinder. And in the next, well, this movie shows up here, so you can see how it behaves. And in this slide here, instead of a BEC cylinder, we have a dielectric cylinder with high permittivity. And you can see a snapshot of the scattering by a cylindrical wave at 1 gigahertz and 2 gigahertz. And the corresponding animation of the wave hitting the cylinder and basically being formed inside the cylinder itself. Another slide that shows the propagation of wave through a dielectric cylinder. This one here is interesting because I have a wave incident into a cylinder, and we are doing animation with the graphic card, and at the same time we are doing the calculation with the graphic card as well. So basically you can see the performance of the evaluation is about 900 million cells per second relative to about 20 million cells per second on the CPU. We have developed a program in which we can get our input to the program using MATLAB as an input interface and output interface also using MATLAB. And then the engine, computational engine, can run using Fortran language on the CPU or C encoder on the GPU. And with this package, we can have all kind of objects, also all these circuit elements. And I'm going to show you here, for example, this is a very simple loop antenna. Is being excited on a very, very old graphic card using 0.7 minute. And when we put EBG structure under it, the same time is being used to simulate the entire structure. This slide shows you the non-uniform discretization on a design of a circularly polarized tag antenna, comparison with other solutions as well, and with comparison with measurements. Bow tie antenna, a very wide band characteristic, and all kind of results that you can get it out of the solver, and dual polarized configuration of the bow tie. You can see still the wide band characteristic, and the radiation pattern in 2-dimension plane and polar format or 3-dimension format. We can also create an array. Here is, for example, one dipole antenna, but the package can mimic this dipole antenna in array configuration and can produce a radiation pattern with different amplitude and phase applied to this configuration. For example, here with uniform amplitude and 0 phase, this is the pattern, and this is the pattern with a steered beam at 40 degrees. The solution is also capable for simulating very, very complicated antenna structure, like the tidally coupled dipole antenna. And here is 5x5 array. And these are the coupling between all the elements. This is 5 arrays, linear array. And here is the comparison between SIMS, which is the finite difference time domain package, the CST and HFSS for the S parameter as a passive S parameter, or the S parameter as an active S parameter. Also, we can have a simulation for larger objects at different frequencies. For example, this rocket here is about 9 centimeter edge to edge, or about 1 meter. And you can see the RCS is being computed by one run at 3 different frequencies. And this is one plane cut. This is another plane cut. And this is basically the orientation of the excitation is a different orientation. We also have an aeroplane that's been simulated. And from the simulation, you can get the result at 2 or 3 different frequency. There is one plane cut, and here is another plane cut. And this plane was basically 40 lambda by 26 lambda by 12.5 lambda, which is not a small aeroplane. This simulation has been done in about 4.6 minutes with 6.6 billion cells per second execution on 2 graphic cards on one computer. So in 2018, our performance on one graphic card was about 4.5 billion cells per second execution. Today, we can perform up to 9.5 billion cells per second execution, up to 6 million cells on 2 graphic cards that are about 2 years old. In addition to this, these comparisons are being done using C and CUDA. Also, we asked our students to start working with MATLAB, and we run the code on multi-CPU and multi-GPU. We got some performance, so I'm not gonna go through it because of the time. I'll be glad to share the slides with you later on. I'm gonna come to the conclusion here and say that finite difference time domain is a very useful technique, very efficient if we use it properly. And we need to rely on the time domain result to look at it first and assess it first before we trust any frequency domain. There are still so many issues that need to be implemented and perfected in this finite difference time domain, specifically if we're working with cylindrical and spherical coordinates. In 2009, we published this book with all kind of MATLAB codes for solutions. 2015, we added 4 more chapters and we updated other chapters. And I would like to stop here by acknowledging the contribution of so many other colleagues and students and current students as well. So if you have any questions, I'll be glad to answer.
Thank you very much, Professor Atef.